like Auckland area that's mainly got cliffed coasts. Other areas have vast quantities of really low-lying land. This is, for an example, the Hauraki Gulf. And it's not the mean sea level so much that's important. It's the surges and the waves on top of that that form the real hazard. So we want to figure out how that low-lying land might react to sea level rise and climate change. And so I've been working on that probably for the last 10 years. And this is sort of summary of interesting things I've learned, and hopefully you'll find them interesting too. Now, so I guess how low-lying land will respond will depend on its profile and how its profile will change. And in particular, I've been interested in areas with mangroves, the whole upper north end of the North Island of New Zealand as Abyssinia mangroves, which is one species of mangroves that actually exists all around the world. And you can see, if you look, here's some plots of intertidal profiles in mangrove regions with the mangroves plotted in green and the profile in blue. And I think that's relative to, that's not relative, that's relative to local datum. But you can see that they really are very different, even with the same species. Abyssinia can be flat-topped and high on the intertidal, or it can be linearly sloping. And it depends somewhat on whether the composition is made up of sand or mud. And so I guess the point of this slide here is that profiles vary very widely between sites, and it's critically important to understand the shape of those profiles and how that develops as we make plans to adapt for sea level rise. So looking at the processes around intertidal coastal land and how it's built, this diagram shows your Abyssinia plant tree with its lateral roots, radial roots growing out, and with these nematophores sticking up. And here's the intertidal flat region down on that side. And the critical thing is here is how will these three regions of water depth change through time. Out here, we've got waves and tidal currents that suspend and advect the sediment into the intertidal regions. Here you've got the vegetation and the nematophore roots that can either increase scour or they can protect the bed and cause deposition. Depending in a very complex way in how those intertidal, the vegetation causes turbulence, whether it causes shear zones at the top of the vegetation, or whether the flow gets pressed through the vegetation or not. And then as we get into the intertidal regions, what are the processes of settling, and finally compaction and consolidation through dewatering processes. So the key thing is the sediment supply greater on the incoming tide than it is on the outgoing tide? Now, if we look at your typical intertidal region, the black line here shows the tidal elevation, and the red line shows the velocity that you normally see in an intertidal region. And I guess we can plot that with the tidal elevation on the vertical axis and the currents on the horizontal axis, with the flooding tide on the right-hand side and the ebbing tide on the left-hand side there. And so we start here at low tide, and as we move up to high tide through the flooding currents and through the ebbing currents, we see that pattern. And the advantage of plotting the plot like this as a tidal stage plot is we can instantly see if the right-hand side of that plot, or of that tidal stage plot, is greater than the left-hand side, and which will mean the flooding currents are greater than the ebbing currents. And we can also see when that occurs. Does it occur closer to high tide, or does it occur closer to low tide? So I just plotted that out to get you used to looking at a tidal stage plot, because I use them a lot. So the first thing is that we've got, Steve Hunt did this paper where he classified the 3 types of tidal stage plots that you might see in an intertidal region. Here we have a case where, now I really apologize, he did it the other way around. So he's got his flooding tides on the left-hand side and is ebbing tides on the right-hand side. So this diagram's reversed. But the first case is in which you get the flooding tide greater than the ebbing tide, but there's not a particular time during the tidal stage that occurs. So you have the flood dominant case and the ebb dominant case here. And here he's then plotted a case where you don't have any dominance of ebb or flood tide, but the currents are stronger at low tide versus high tide. And then the left-hand side, that might happen where you've got a very tidally dominated case where the tidal currents are stronger in the channels at low tide. In the right-hand side here, you might have a case where there are waves on the high intertidal and they scour down the bed and cause the bed currents to be stronger at high tide. And obviously in this case, in the right-hand side case, then the sediments won't scour out at high tide because the bed shear stress is still high. Whereas in the left-hand case over here, the currents, you'll get settling at high tide. And then he pointed out the last case here, where you get a spatial distribution in the strength of currents. So here you might get higher currents in the channels than in the intertidal regions. In the right-hand case, you can get the opposite occurring, where you might have higher currents in the intertidal than in the channel. So in this left-hand case, you would get scouring in the channel, which would then settle on the high intertidal. And the right-hand case here, you would get scouring on the channel, and then it wouldn't settle on the high intertidal. So the idea is that you can use the shape of these tidal stage plots to infer the patterns of sediment transport that you might experience over an intertidal region. And so this is Rebecca Hohe's MSc thesis, and she looked at the mangrove profile in the Firth of Thames, which is an area that Andrew Swale has worked a lot. A number of people have worked a lot. And it is a kilometer-wide region of mangroves. And the profile is high intertidal all the way out to the edge of the mangroves, and then it drops off. And so she did a Delft 3D profile model. Well, it was a full model, but she extracted a profile from that and plotted out these tidal stage plots as you moved from outside the intertidal here over up the fringe, and then as the colors go red, right into the center of the mangroves. And she could show that at the top of the intertidal, the currents were flood dominated, and at the lower region, they were ebb dominated. So that was the classic shape of the tidal stage plot over one of these intertidal areas. And she could also show that the flow was generally flood dominant at the top and ebb dominant at the bottom. And so you would expect sediments to import at the top and export at the seaward fringe, and that you would have a null point right at the division between those two, which corresponded quite well to where the morphology, the change in slope of morphology occurred. And also had this strong reduction in amplitude inward, which would also cause settling inward. She could then also run this with and without vegetation. So she could take the vegetation out, because it's a model, you can remove the vegetation from Delft. And this shows the currents, the water level, and the stage plot, the top plot, at the edge of the intertidal, and then moving inwards across that fringe. And so you can see that the currents diminish rapidly even without vegetation, and that's just due to the effect of bottom friction. And then when you add the vegetation, of course, it diminishes even more. And so even without vegetation, it causes strong attenuation. And people kind of, who look at mangrove sites, they kind of think that the mangroves and the vegetation are doing all the work, but it's actually the friction as well that's doing a lot of the work. Vegetation also causes drainage, a delay in the amount of how quickly the water drains off the intertidal, and the vegetation strongly enhances the ebb dominance at the fringe and the flood dominance inside the mangroves. So that's quite interesting that the ebb dominance actually, the vegetation seaward of the fringe, so the vegetation landward of the fringe causes the ebb dominance to increase outside of the mangroves, which is quite interesting because people who study mangroves also don't see them as having an effect on the tidal currents outside of the mangroves. Okay, they think that they just affect us locally. And so the difference with the and she could put different amounts of vegetation in the model and got quite a different effect on the ebb dominance. And the way she explained that is that basically the currents, the vegetation here traps the currents, and the more the vegetation traps the water in the top of the intertidal, the greater the hydraulic gradient that you have across that, which then drives more dominant ebb currents on the outward tide. Okay, so that was all with models. She didn't use any data at all, apart from to do a bit of calibration of her model. Then we could go on and look at Steve Hunt's PhD work here, where he went and to look at those tidal stage plots in the Whangaroa estuary, which is Raglan estuary on the west coast near here. And he plotted out transects in the intertidal on one of the arms of the estuary here. And he could show here's a transect across, it's actually a hypsometry curve, but it's similar to the transect on the left there. And he could show here, the blue one, this blue line here was the tidal stage plot in the channel. The red dashed line is the tidal stage plot on the intertidal. And then there was the upper intertidal region with the pink line. And he could show again a drastic diminishment of current as he moved shoreward, and also this switch to flood dominance as he moved up over the intertidal. And this was a situation with no waves. And here he's plotted bed shear stress, not currents. And then if you look at the same transect, only with the effect of waves, you get a complete reversal, and you get the lower flows on the lower shear stress on the lower intertidal and much higher shear stress on the upper intertidal. And so the waves cause scarring of sediment seawards, which a number of people have shown as well. Now, if you go back to the Firth of Thames site and look at the water level measurements that we took during our experiments I did with Julia Mallarney and Eric Horstman, and John did that for one of his chapters of his thesis. He looked at the current meter right across the intertidal. And what he showed in this transect is he moved from the outer region to the inner region, the intertidal, is he showed the measurements of how much the tide storm surge was in case it was a very high tide. That storm surge varied as he moved across the intertidal. And so that dropped probably around, I think he measured it as about 30% reduction across a kilometer of the storm surge that happened during that deployment. Now, the interesting thing is he then went and John developed a little analytical model to explain this drop in the vegetation that was simply related to the frictional drag balancing the water gradient across the intertidal. And the model worked really well. This shows the maximum water elevation and the distance from the stop bank, so seaward and landward. And the dashed line showed his model results, and the solid line here shows his the water level observations from seaward to landward side. And he got really nice correspondence with that. Now, the interesting thing is that he could then play around with changing the dimensions of his intertidal area with this simple model and to change the amount of storage area. And so he did that with 4 different cases. One in which he made a very, very small intertidal area, so quite narrow, only half the size of the wavelength of the tide. And then he made a bigger one and bigger and bigger one. And the interesting thing is all these 4 cases have exactly the same amount of friction, but different amounts of intertidal storage. And he could show that the intertidal storage was much more important than the actual density of the vegetation in determining how much that tidal wave diminished. So it's the overall size of the forest can be much more important than the amount of attenuation. And so it's not like a wind wave in its effect on the wave amplitude. And the storage capacity is more important than the dissipation. It's a big, big scale wave, these surges. Okay, and so that links us back to this shape of the profile. The shape of the profile and how much storage is there and how much storage is contained in the profile is obviously critically important to how this behaves in a storm system. Okay, then he went, this John, again, I'll put his face there, so I think he might be listening. Then he went to a different site, and this is in Tauranga Harbour on the east coast of New Zealand, and found another mangrove area that was just about the same width. So it should diminish the tidal wave just about the same amount. And he looked at the propagation of the tidal wave across these stations here, marked here. And he found that there was basically an indetectable amount of attenuation of the tidal wave. Okay. And here's the profile here that he looked at. That's from the LiDAR elevation map. Well, maybe you can say maybe the vegetation wasn't as dense. Well, the vegetation was actually much more dense in that it was very shrubby mangroves that kind of existed, you know, that kind of lay flat. Mangroves do this thing called canopy dislocation, where they move sideways and their stems become very contorted. And so he decided to play around with these conditions using the Delft model and to put the vegetation in Delft. Now there's a big difference between putting this in Delft and putting something that has just got stems sticking straight up and little nematophores sticking straight up, which essentially look like cylinders that you can measure the dimensions of and put them in quite easily. And so he managed to figure out a way of doing this by looking at the ratio of stem width to height. And we went and measured, I don't know, 20 of these trees, and also the length and orientation of those stems, and found some relatively consistent patterns so he could model a typical tree. And so put that typical tree dimensions into Delft. And so he's, yeah, I thought that was quite cool. And he found the way to do that from what people have used on poplar flow, or poplars growing on the sides of rivers, who also use a typical shape of a poplar tree to measure the effect of that. So he put that in the Delft 3D model and got fairly good match about this. And you can see the dashed lines on the top panel here are the model, and the solid lines are the observations. So you could reproduce the fact that even with those very, very dense vegetation put in the model, it didn't cause any attenuation at all. He also had some current meter measurements, and those are plotted down here with this black line is the model, and the red, blue, and yellow lines are 3 different observation points that were out here in the channel. And so what was happening here was that the 2 channels that drained the network, the mangrove area, the channel network that drained it, were basically channelizing the flow, and it wasn't flowing through the vegetation barely at all. And so the frictional effect of the mangroves was pretty irrelevant. And in fact, he could make the mangroves even more frictionful or more dense in the model, and all it did was channelize the flow even more. And this is the water level elevation up at the top, and this is the flow diagram at the bottom. And you can see that the water elevation has strong lateral gradients across the forest associated with these 2 channels. So then when we go back to our model where we had that Firth of Thames, from the Firth of Thames, there's barely any channels in the Firth of Thames. And so the channels actually play a much stronger role in the ability to attenuate storm surges than the mangroves themselves. And that just shows a slice of the water velocity through those channels with a really 4 times the actual tree density, and then just the normal tree density. And you can see how much it gets even more channelized when you make the trees more dense. And this just shows some velocity plots across those 2 channels. So at different points along the mangroves. Okay, so then if you took the channels out of the model, the attenuation was not quite as dramatic as in the Firth of Thames, but he still got his attenuation back, proving the point of the role of the channels. And then the next thing he explored did it have to do with how high the water level was compared to how much of the water was occupied by the vegetation. So if you have a really big storm surge over your canopy, your vegetation becomes a smaller and smaller fraction of that storm surge. And so he could do that by creating bigger and bigger flood waves through the mangroves. And you can see that indeed was the case. When the flood wave was quite small, this dark green one, it caused a really large, well, quite large reduction in the flood amplitude. But as you increased your surge size, the attenuation capacity of the mangroves got lower and lower and lower. And what we don't tend to, you see some people saying that the effect of mangroves and storm surges is, 20% reduction per kilometer, but they don't, and then they extrapolate that to larger and larger storm events or storm surges, but it's not actually true. They behave very differently depending on the size of the surge. And then he went back to the intertidal storage question again and made the intertidal area with different slopes. So if it has a strong slope, it doesn't have a lot of storage. And if it has no slope at all, it has a lot of storage behind. And you can see yet again, he found a strong effect on the amount of storage on how much the surge wave was attenuated. Okay, so moving on. So that sort of looks at the hydrodynamic processes around those intertidal areas and how that and how we're inferring what might happen to the sediments just by looking at the hydrodynamics. But then we started to think about, well, how do the sediments behave as well? And the first thing we are interested in is when we were out collecting those measurements across the intertidal in the Firth of Thames, we also were looking at doing some measurements of the critical erosion stress so we could run the Delft sediment model as well. And so we went out with aromas device, which is basically you take a core in the field and you put an impeller in the field, and then it's got an OBS, and you step up the propeller at different known threshold velocities, and you basically observe when the sediments start to get entrained off the bottom, and that tells you what your critical erosion stress of this site would be. And so we brought this out to the end of our site, Andrew Swales' site, at the end of the boardwalk, and we set it up, and we started collecting these cores and doing these experiments out on the end of the mangroves, right in the middle of the mangroves. And we could collect cores, and they take about half an hour to collect each. And so we do a couple, and then the tide would come up, and we'd have to stop. And then we do a couple as the tide drained down. Now, the grain size in the Firth of Thames is very, very fine. It's very muddy, and it varies almost not at all. We've taken, I can't remember exactly it's something like 4 or 5 or 6 microns is the median grain size, and it barely changes at all. But then we started to get vast differences in the erosion threshold in the areas where we collected the cores just as the tide drained versus the ones that had been out all day. And we thought, wow, gosh, I think baking of those out in the intertidal has more effect than anything to do with the erosion, to do with the percentage of mud or the grains or anything like that. And so Hugh decided, this is Hugh Nguyen, he decided to take that on for his PhD. And so he decided to explore that in a lot of detail. And he collected cores over a wide range of, so from the same site, sorry, for the same location. So they were all pretty much exactly the same grain size. They of course varied a little bit with the amount of chlorophyll, just a little bit. And he brought those back into the lab and he put them in various cool rooms with temperature controlled rooms. And he then measured the critical erosion threshold. He had to do it, these measurements can be quite variable depending on what the surface of the sediment looks like. And so you have to do quite a few of them. So it's quite labor intensive work. But he showed after having them exposed to 6 hours only, that the exposure temperature could make a vast difference to the critical erosion threshold. And so it could increase by double between 8 degrees and 40 degrees. So then he went on and thought, well, it's not just the temperature, it's how long it's been exposed. From the temperature experiments, he realized it wasn't really temperature was what was the effect. It was actually the water content of the surface of the sediments. And so the water content affects the plasticity of the sediments. And so he decided to do the same. And I should point out that the Firth of Thames site has a lot of spring neap variability. The neap tide, I think, is only about ½ meter, with the spring tide goes up to almost 3 meters. And so in the high intertidal, between spring tides, those sediments can be exposed for up to 14 days, which is quite a long time for exposure. And so he took the typical exposure areas of the intertidal regions in the Firth of Thames and ran controlled experiments over that 14-day range. And so that's what his sediments looked like over those 14 days. And so in this time, he exposed them to naturally varying temperatures. So we did the experiments twice, once in the summer, early summer, and once in the late summer. So it's like, I think they were about 5-degree difference in temperature, but just the natural varying temperature cycle. And he covered them so that they were in over a shelter so that they didn't get rained on. And so you can see that the dashed line here is the erosion rate, and the triangles or the solid line is the critical erosion stress. And so you could see a dramatic difference again between exposure time and the critical erosion threshold. And so if he took those measurements of exposure and temperature and created one model that had exposure and temperature in it, he could get a generalized function for the critical erosion stress and the erosion threshold. And he did it for both high chlorophyll and low chlorophyll samples. Now the tau, the critical erosion threshold, was pretty much well modeled with a linear fit, whereas the erosion rate was more an exponential fit. So he developed a relationship between exposure and temperature. And with the help of Zheng Zhu from Hohai University in China, they put that erosion threshold and temperature into the Delft 3D model. And so he could model the effect of a profile development of that exposure. And so this shows a couple of tidal cycles in the bottom, and here's the model with no effect added. So this is the critical erosion threshold, and this is the cross-shore distance across the Firth Thames transect, and the white areas are areas that are exposed, and the blue areas are the areas that are underwater. And that's the erosion rate, and then plotted behind his face there, sorry, is the suspended sediment concentration. So as you can see, as the tide comes in, you get a time when the currents are maximized, which causes a suspension of material, which is then put into the mangrove forest and deposited. and then the returning currents aren't so strong, so there's a net delivery of sediment into the mangrove forest. And so he could add the critical erosion threshold effect, and then he had to allow that effect to decay back as the tides got re-inundated. So this is with a little bit of an effect, and then more of an effect and more of an effect. So he ran these multiple scenarios to test the effect on the profile development. And so this is the result that he got. This is the bed level change over a year of bed evolution. And the dashed line here is the model with no effect. And you can see that the intertidal builds up most on the high intertidal. The gray area is the intertidal region. And so when you add an effect, when you add the effect, where the bed all through the intertidal region gets stabilized, you can see that the buildup happens on the lower intertidal rather than the upper intertidal. So it changes the way in which the profile develops, and it develops more quickly on the lower side. And so back to these tidal stage plots, you can plot out tidal stage plots to understand the processes that are happening here. And this is actually a stage plot that's done with sediment flux rather than currents. And so you can see the ebbing tides at low tide. At low tide, you have ebb dominant flows, and at high tide, you have flood dominant flows. And then as you move up over the intertidal, you just have flood dominant conditions. So again, the dashed lines are the lines with the with no effect added. And then you can see the dramatic difference that happens if you add the exposure effect. And you can see exactly why it all deposits at the lower intertidal region when you add that effect in. So that's pretty interesting. So that really says that the exposure conditions really make a big difference to how your profile might evolve through time. Okay, so with the normal effect, you have quite a good supply at the edge of the intertidal, moving up to the high intertidal. But when you add the effect, the supply quickly disappears because there's no scarring at the lower intertidal because it's been baked on. Okay, so that moves on to the final bit of research that I wanted to show you, which is the work of Robert Truscoden, who is one of the Intercoast Brayman students that we had visit us in New Zealand through the Brayman Intercoast Exchange Program. And he came out with his Nimrod device. So he comes from Akin Koff's lab, and they're engineering geologists that look at the stability and consolidation of seabed sediments. And they developed this device called Nimrod, which allows you to measure the pressure and the friction along the sides of this device when you drop it into the sediments. And from those measurements, you can work out what the consolidation is of the sediments. And you can drop it through water, or you can drop it in land. So we took a boat and we dropped it off of the intertidal areas into the water. And then we made a big, what do you call this, a tripod, and dropped it from the tripod into the sediments. And that sort of sliced through the Nimrod. Now, you could see quite a major contrast between the Nimrod being dropped in the underwater sites and the boat sites from the mangrove sites. You can see that the tip resistance was much higher in the mangrove forests, and also the side friction was higher, and the instrument, of course, didn't penetrate as deeply in the mangroves than in the boat transit. Remember, there's absolutely no difference in the sediment grain size from each of these sites, or trivial difference in the mangrove, in the sediment characteristics. Now you can, one of the things the engineering geologists do is to classify the soil behavior type in terms of its, and these are the classification diagrams that they normally use. And so this is the tip resistance on this axis, and then the normalized friction ratio on this axis. And so whether you, which region that you lie in one of these, you get classified behavior type 1, 2, 3, 4. And most took his measurements classified in behavior 3 or 4 in those soil classes. But the ones that he took in the mangroves, these ones up at the top, were all classed as 6. So it's changed its soil classification completely. And here on the right-hand side, he put the soil behavior type, okay, as a distance from the edge of the mangroves, where the interface is plotted with that line. So the ones up at the top are in the seaward side, and the ones in the bottom side of that line are in the landward side. So you can see that there's a definite change in the soil behavior type as you move in over the mangroves. We had measurements of the number of trees and number of roots, so the vegetation density, as you move across the edge of the intertidal areas. And so the vegetation density obviously increased as the mangroves were more established. And he correlated that with the quasi-static bearing capacity and the coefficient of consolidation, which are basically 2 measures showing how consolidated the sediments are. Now, what of course he couldn't tell what the effect was caused by, whether it was caused by the physical presence of roots or whether it was caused by the dewatering activity of roots, because roots remove water from the sediments and cause them to consolidate more quickly. But then when we add that to the baking effect and then the consolidation of the mangroves, that is a sort of a double whammy. It makes the sediments even less likely to be removed when they establish inside the mangroves like that. So that was basically what we've been doing so far. And I guess the more I study this transition zone across the intertidal, the more intriguing I find it. And the more interesting that interplay between the mangroves, the roots, the baking, the exposure becomes. And in the beginning, I was mostly interested in the hydrodynamics and how they really can change a lot across there. The asymmetry changes dramatically, the attenuate dramatically, both because of the vegetation and just because of the heightened friction in the intertidal. As John shown, the very large scale morphology also has an effect. Those big channels make a big difference, and the amount of intertidal storage in the back region, whether there's a backstop area back here, do you go back to a wall, do you go back to steeper topography like we often do in New Zealand, because these areas are infilled river valleys, and so that you get the old river valley bank at the edge of the intertidal. But we can't infer everything from the morphodynamics. There's a lot of the subtlety of the sediments, the way in which the sediments change with exposure, and with the mangroves is also a dominant force. And you can see in New Zealand, we've got an even more dominant force happening in that a lot of our mangrove areas are getting managed because they're expanding, and people don't like that so much. That's it. I've got a lot of acknowledgements because of the co-supervisors that have helped me with the students. Achim for Robert's work. Giovanni, Dean Sandwell's been helping John Montgomery, and that's funded by the Natural Hazards Platform. Rebecca Hohe's thesis was done with Eric Horstman and was funded by Waikato Regional Council. Hugh is with Conrad Pildich and Zheng Zhu. Steve's thesis was Commonwealth Scholarship, and finally the water level measurements we took at the Firth Thames were funded by Marsden Fund. And that's it. Questions?
Thanks very much, Karin. If anyone has any questions, you're welcome to either post them to the chat, or you're also welcome just to ask Karin to make it a bit more interactive. So far, I don't see any here. I guess I could start possibly. So forgive me here if I completely misunderstood it. But I was looking at it from a modeling perspective, and what was coming out for me, it seemed that bathymetry was playing a much bigger role than whether or not we could accurately model the vegetation in there. And I think of some of the sort of future sea level rise scenarios that we're doing. Can we ignore that then and just have a good map of bathymetry, or can we possibly, based on that latter work you showed, have some form of different friction factor or soil strength that it can account for those processes versus having to know how many mangroves and the density of them.
I guess I got really excited and wondered whether you could just match, like just map from an air photo, the ratio of vegetation to channelization and plus the storage from intertidal and get a very good idea of how much the attenuation would be. But I haven't tried that, but theoretically, I spent a long time measuring vegetation and it's really boring. And I was very excited to see that perhaps it wasn't so necessary.
And it's a very hard thing to do and labor intensive. So if it's showing that we could maybe get something from an aerial photo or
just a generic roughness value,
get an offset, that makes it far more easier, I guess, for us to be able to give an idea. Anna's got a comment or a question. Anna, do you want to just say it or do you want me to read it? Oh, you're on mute if you're talking.
Yeah, sorry. I was just stopping the recording, so we don't have the